All right, so I'm gonna take the next literally hour and 10 minutes, that's what it's gonna take, to present to you what the current draft proposal for generics looks like. The proposal has really, I think, stabled out, and the language team is pretty happy with what's here. But I'll give you my opinions along the way as well. There's 3 links here that I'm gonna provide. The first link is going to be to the training material that we're going to be looking at tonight. The second link is a link to the draft document. And the third link is a Google survey that allows you to give direct and anonymous feedback to the language team that's working on this draft proposal. So what I'm showing you right now is the training repo for where the training material is. Now, you can see here that there is 13 different examples. We don't have time to go through all 13. That would take a half a day. We're not going to do that. My goal is, not my goal, but what we're going to do is go through the first 5. When I get through the first 5 in about an hour, then what we're going to end up being able to do is really see a good 85% of the draft proposal. And the syntax and understanding it and understanding where it's going. But there's a README here that has a few links as well. This first link here is another link to the draft proposal document. You can see it was updated about 2 days ago, and I haven't even looked to see what changes are here. I'm going to have to do that sometime this week, though I sent an email out to Ian and Robert and they said nothing's significantly has changed. So I think they did some typos actually, to be honest with you. I think that's all it's changed since August. But that link is to the draft design document. Now, there's a link here that says Go to Go. And what this is a playground specific to allowing you to experiment and prototype with the new syntax. And then during this talk, if you have questions and you come up with some code that you want to share or talk about, put it in the playground and then you can post that link in the chat and we can talk about it. Now, I'm not going to be using the playground. I'm going to be using the Go tooling directly on my computer. And I'll show you how you can install that if you want. This document also provides the high-level overview of what the draft proposal for this first release of generics is going to contain. This list can still change between now and that release, but this is pretty much what's being focused on for a first release. I'm not going to read that. You can read it. You can see what's there. There's also an emissions list for just this first release of generics. It doesn't mean that these things won't make it in a second, third, or fourth release of generics. But the chances of this being in the first release is pretty slim. You can read that. You don't need me to read it. Give you an idea of what you're not going to see right now. I do have some extra blog posts and reading in here. I'm just about to publish my 3rd post for the 3rd example that we will go over tonight. Those other posts go into more detail on the first 2. And then these are the instructions to install it locally from source if you want to play with this Go tooling locally. Now, let me just say 2 more things before we get started. This Go tooling is literally just that. It's tooling. None of this has been implemented in the compiler right now. This tool is a transpiler. It's taking the new syntax, converting it into something that can be built and run as a Go program. So there's lots of, if you look at the source code that's generated, there's a bunch of interesting kind of back-end functions and stuff they've written to make it work. So it's purely a transpiler. Don't try to use this yet for any production level code. But the language team is now starting to investigate and prototype an actual compiler implementation. So that's kind of exciting. What I recently heard from the language team is that if everything goes perfectly between now and August of next year, which will be version 117 of Go, we could see a compiler implementation being released. So I think August of next year, 21, version 117 ago would be the earliest we can see it. If no major roadblocks comes up between now and then, we're looking good. I still lean on the 118 release of February 22. I think that's very realistic. But August could have something in it that could be fun. Okay. With all that being said, and time always against us, I'm going to jump in here. Now, my goal is to walk you through the syntax and really try to share with you even why we need new syntax, and how the syntax is really working towards making the code that we write today more readable and more comprehensible by more developers. That's our goal. The goal is not to write code that performs better. In fact, I'm going to make an argument that depending on how they actually decide to implement this in the compiler, we may not really see better performance out of your generic functions than your concrete. So let's not focus on this as a way to write code that's fast. This is about trying to write code that is more readable, more comprehensible. And that's what I want you to focus on when I show you the syntax. Now, the way I like to approach looking at and learning the syntax is by starting with functions that we can encode, that we can write today, and then looking at maybe some of the limitations of what that code is and how generics can help. So if we start here on line 13, what you see me doing is writing what I'm going to call a concrete function because it's asking for concrete data. And this function is called print numbers. And what it does is it takes a collection of integers based on our important data structure, the slice. And it allows, what it does is it ranges over, or does that linear traversal over that collection of integers, displaying each integer one at a time with a header at the beginning and a carriage return line feed at the end. So it's 5 lines of code to write this print numbers function that can take this collection of integers. Now, I'm going to make a big, bold statement here, and I'm going to say that just about every Go developer, even those new to the language, can read and comprehend what this code is doing. And I feel confident about that because this code, since it's working with this concrete data type, can really leverage the language mechanics and semantics. And we know already, especially if you Go developer, how the language mechanics and semantics are really simplified to make sure that we have this high level of comprehension and readability. So I think even if you if never even seen Go code before, and you've never seen the concept of a for range mechanic, I think you can read this and comprehend what's going on. And that's the key. But this is a concrete function, which means it accepts data based on what it is and only what it is. And right now that can only be a slice of integers. So if I want to now write a print function that can display a slice or a collection of strings, since the input parameter is changing its type, we need an entire new function. So here I've written a function called print strings. And I think you can see clearly that this is really the same 5 lines of code that you saw here. The only difference really is that I'm changing the variable names to be more in line with the data type, and I've changed out the header information. But really it's the same 5 lines of code. But one nice thing about this being the same 5 lines of code is that this code is as readable and comprehensible as the print numbers. And as you know where I'm going, if I wanted to now do this with floating point numbers, then I have to write another function. But again, we're getting high levels of readability and comprehension, but what are we losing? What's the trade-off? Well, the trade-off is that we're going to need to be managing a lot more code and a lot of the kind of same code. And so, you know, the maintainability, maybe there's some loss in that. So then, you know, you're thinking about the trade-off here between the readability, comprehension, and the maintainability and minimizing the amount of code you need. You know, we can run an experiment and then kind of ask ourselves, well, is there a way to consolidate these 2 functions into a single function where we can still maintain that high comprehension and readability, but also gain back some maintainability? And the answer actually is yes, if we use the language mechanics behind type assertions. Now, there's two things here that are going to allow us to write a single print function that can handle that slice of int and slice of string. The first thing is we've got to be able to pass a slice of int and a slice of string into a single function. Now, what this requires is that we write a polymorphic function, a function that asks for data based on what it can do, not based on what it is. Now, the data that we want to pass here doesn't really do anything. So what we're going to do is leverage the empty interface to be able to accept data and any data, but the idea that it doesn't do anything, right? The empty interface says nothing about the data and doesn't really define a constraint on behavior. So this is going to be a way of us being able to pass data into a single function in a generic way. Now, we're going to be blind to what the data is because it will be decoupled inside of this empty interface, but it does open up the ability to write a single function. And the mechanic we're going to use to know what data we actually passed into this function is the type assertion, which is going to really have to be a runtime check. And so what we're going to do is use a switch here and say, if the concrete data we passed in using a case statement was a slice of integers, then we'll execute this linear traversal. But if it was a slice of string, we'll execute that linear traversal. And we could add more cases for more types. And still, there is some code duplication here, right? Because the for range is now tailored to the specific collection type that we have. But we did get a little bit better in terms of consolidation, but it's not really a generic function, because if I want to now work with a collection of floats, I've got to write some more code. We see that. So then the question becomes, well, is there a way to write an actual generic version of print in Go today that I can pass that slice of int, slice of string, slice of float, a slice of user, and perform the linear traversal and get an output? And the answer is, well, believe it or not, yes, there it is. I'm calling it print reflect, because in order to write a generic version of code today, we're going to need the standard library and we're going to need the reflect package. Now, if you notice, this is also a polymorphic function. It's using the empty interface to accept a slice or an integer of any type. In fact, data of any type. The concrete data is not constrained, right? There's no restriction on the concrete data we can pass in because the empty interface doesn't define any behavior. But if we want to use the reflect package now, we have to kind of walk away from our language mechanics and our language syntax and now work with an API. And so on line 58, you see the call to reflect.valueOf, where we pass the interface value through, and that's going to let us now inspect at runtime the concrete data stored inside of V. We can do things like validate that the data we passed in was a slice, because if somebody doesn't pass in a slice, there's nothing we can do. There's nothing to iterate over. We return nil. In this case, we would just return. We're not returning anything, which actually is a little bit of a different semantic from the other print functions. But, you know, it's like almost passing an empty slice in, isn't it? Okay. But once we know it's a slice, we can't use our for range mechanics, but I can iterate in a variable named I over the length of the collection using the built-in method len. And then I can index over each item in the collection using the index method. And then I use the interface method to get that concrete data back, and I can put it on the print. And essentially now we went from 5 lines of code to 8 lines of code. We went from using our language syntax and mechanics to using an API. And unfortunately, I would argue that this code isn't as readable and as comprehensive, right? it's not as readable and isn't as comprehensive as the other 5 lines of code that we wrote. Now you have to learn and understand an API in order to read this code. So we've lost some of that readability that I'm really high on here. But at the same time, this is a generic version of print. We can print a collection. Now, a big reason that we're able to write this is also because the print function from the func package uses reflection. They use reflection to define some defaults around how to print a value of any given type. So we're gaining the benefits of reflection here also inside the print function to make this work. But I think the big trade-off is that to write this generic function, we have to use the empty interface, which means that we can't really type check anything at compile time. We have to validate at runtime that we even got a slice, because somebody could pass anything in here. And then we can perform these kind of linear traversals using an API. I want to get back to the readability of code. I don't want to lose it, not for the sake of I want everything. I want readability and I want maintainability. And I think this is where generics comes in. Because what generics are going to be able to do is allow us to use our language semantics and syntax, our language mechanics, to write code, but to be able to also gain that maintainability, not having to write many different versions of the same code depending on the data types that you want to support. So we do have a generic version here, but let's take a look at what a generics function could look like in Go based on the current draft proposal. Now, the one thing I want you to notice first is that these are the same 5 lines of code I started with, right? A little label, a for range loop, the print in the middle, and then the carriage return line feed. This code is back to using our language syntax, our language mechanics, because this code is written with the idea that we're operating on a concrete type again. Our generic functions are polymorphic, but not on a traditional polymorphic function, because our traditional polymorphic functions ask for data based on what it can do. This function still needs to ask for data based on what it is. And so this polymorphism, in a sense, is now at the compiler level, right? It's going to be at the compiler level, right? They call it parameter-based polymorphism. But I want to get a better understanding of the syntax here. And I think the best way to do that is to remove it and kind of look at this function as a regular function we can write in Go. So if you look here on line 81, I'm writing a function named print. And on the surface, it looks like I'm asking for a slice of type T. But you really know what I want to do here, right? I don't really want a slice of type T. What I want to do is tell the compiler that I want a slice of some type T to be determined later. That's the key. The key is I want to tell the compiler that T isn't a real type. It's a type that's going to be substituted later for something that's real, to be determined later. This is what I really need to do. The problem is the syntax that I'm showing you right now assumes that this T is going to be a type that will be defined before I hit the build button. Before I try to compile this code assumes that T is going to be defined like I did on line 81. The problem is that's the opposite of what I want. I don't want to define T prior to compiling this program. I want to determine what T is at compile time based on either being able to infer the type or me explicitly providing that type information. Now, this is why we need some new syntax, because this syntax in and of itself won't work because we have that backwards compatibility problem. This syntax again assumes that T will be declared by you or me, okay, somewhere where the compiler will know about it. So how do we tell the compiler that T is going to be a generic type? to be determined later. This is why we need the new syntax. Now, the draft document says this is how we're going to declare T to be a generic type to be determined later. When it comes to our functions, we're going to apply a set of square brackets against the function name. And then we're going to list out the names of those generic types that we want, in this case, T. And then the draft says that we have to apply a constraint against T. And if there is no constraint on what T can be, then we use the pre-declared constraint called any. And any is saying that T can be substituted for anything. There is no constraint against it. I'm going to get back to constraints later, but since the syntax demands that we apply a constraint to a generic type, you're going to see me using any. And it's this square bracket syntax now that is telling the compiler, don't look for some type named T because you're not going to find it. T is a generic type declared in this list with the square brackets. It can be anything. And at compile time, we're going to need to substitute T to be maybe an int, maybe a string, maybe a user, basically a concrete type. And since T represents a concrete type, guess what? We can write code already as if it is. We can write code as if it's already an int or a string or a user. And this is the best part. This is what's beautiful, because we're back to writing code using our language syntax and our language mechanics, which I'm saying makes code easier to read and easier to comprehend. And this is what we want. And so we need this set of square brackets to define the generic type list related to this function. And we're going to define that it can be anything. Now, let's see this code run. In order to run, I'm going to have to transpile it into a working Go program. And that's what that Go tooling does. So you see in main, I'm going to construct a slice of integers and a slice of strings. And then I'm going to pass that slice of integers to our 4 functions that can work with it, that slice of int, and then I'm going to pass it to the 4 functions that can work with the slice of string. Remember, print, reflect, and print are generic functions. They can handle a slice of any type. Now, I come back to the terminal window here. I'm going to switch over to the O1 folder. Make this a little bit bigger. And what you're going to notice that when I type Go version, you're not going to see 1.15.2. You're going to see that I am running a build from about 8 days ago from source. And this build of Go that I have has the Go tool. So if I want to run this program, I'm going to say Go tool, Go to Go, issue the run command, give it the file name. Notice it has a Go to extension. The Go tool will transpile it, build it, and run it. And now we can see here that I have the same output for each of these functions. But what's the real win here? The real win is this, right? The idea that I can go ahead and now construct a collection of these floats. And instead of having to write a new implementation like print float or add a new case to print assert, I could take these floats and pass them to our 2 generic functions, print, reflect, and print. And now, if I run this again, you can see I've got an error on line 98 because I didn't say float 64 because I'm not perfect. And here we are. Now I've got a true collection of float 64 numbers. And there we are. We've got the display of these individual floating point numbers without having to write any more code. And I think the important part here is that we could do it with reflection. We're doing it today. but it does make code harder to read, which is going to make code harder to maintain and understand. We do have to write a polymorphic function that really doesn't ask for any constraint on behavior, which requires more runtime checks that the compiler can't catch up front, which could produce code that increases some misuse and fraud and mistakes we can't catch till runtime. Or, thanks to generics, we can write a concrete version of print that is generic, using the same language, syntax, and mechanics we would if this was specifically for a slice of int or string. But to be able to tell the compiler that, no, this is a slice of T, where T is a generic type that can be anything that is to be determined at compile time. Now let's talk about the to be determined later, right? At compile time, later. How do we do that? Well, at this point, the big part of the implementation is going to be able to infer the type. And in these cases, to this call to print, the Go tooling has been able to infer that T should be an int, or T should be a float, or T should be a string. And it's able to do that because we're using the generic type identifier as part of the first argument of input. So when the compiler sees that we're passing a slice of int through, the compiler can say, oh, that must be an int. When it sees that we're passing a slice of string through, it says, oh, that must be a string. And so there's a way in this case for the compiler to infer the type. But what if we weren't using T as an input, right? An input argument. Maybe we're using T in the body of the function. What happens if the compiler doesn't have the information it needs in order to be able to infer the type information? Not a problem. Just like these parentheses define a set of input arguments, right? Data that we can pass into the function. These square brackets also represent a way for us to explicitly pass type information for T when the compiler can't infer it. So in other words, I could come in here and explicitly state that T is going to represent an int and bypass the whole inference thing altogether and just tell the compiler that in this particular call to print, this better be a slice of integers or fail. This should be a slice of float or fail. It doesn't make sense here to do that because the compiler can infer the type. You can see that this still compiles with that syntax. It doesn't make sense when the compiler can infer the type because we want, in this case, the function call to resemble a traditional function call because that lends itself to better readability. But I do want to share with you the fact that we can pass explicitly what T is. And this is why I'm saying to be determined later. Because either we can determine T at compile time through the inference algorithms, or we can just explicitly pass T and tell the compiler on that call right there what T is going to be. We have both options. But being able to infer is really going to be an important aspect of the compiler implementation and the usability of generics. Okay, so we've seen our first generic function in Go. And we've started to understand why we need the new syntax. Now, a lot of times, right, if we're going to write real world programs, then you're going to be defining your own data structures. Go is a data-oriented programming language. And if you take any of my classes, you'll hear me say all the time that it's all about data-oriented design. If you don't understand the data, you don't understand the problem, because every problem that you're working on is a data transformation problem. So we're going to be defining types, user-defined types. And we're going to want the generics to kind of be a part of that type declaration. Now, there's two ways to declare types in Go. We can declare a type using an underlying type, or you can declare type through the use of the keyword struct. And they both have interesting semantics behind them. So let's start with defining a user-defined type using an underlying type. Now, In this case, on line 15, I'm defining a type named vector int, which has an underlying type of a slice of int, its base type. What this means is that a vector int is essentially modeled, the data is modeled after an existing type here, the underlying type, which is a collection of integers. Same thing here on line 24, vector string is using an underlying type, which is a slice of string. It makes vector string basically a slice of string. Now, to make the example more interesting, I've added a method to both vector int and vector string. And I've called that method last. Now, what this method does is it returns the last value in the vector, which is really the value at the highest index position, and then returns that value. So this implementation of last returns integers. This implementation on line 26 returns strings. If I were to do this for a vector float, that would be returning a float. And again, the 4 lines of code I'm writing for last for my int is the same. We check to validate if the vector is empty. If it is, we return the literal 0 value for an int. Here we return the literal 0 value for a string. This is an idiom we use a lot in Go on the returns. Try to be as literal and clear on what is being returned. And when the error is being returned, use the 0 value for all other arguments. That's what we're doing here. And then if we're returning out something like the value because it works, we use the 0 value nil for the error interface. So this is an important idiom and guideline that I've written in this code. But once again, outside of the fact that the empty string is the 0 value for a string and a 0 is the 0 value for an int, these 4 lines of code are essentially the same. So we can walk back through and say, well, could we do this in a generic way today in Go? And there it is. I can define the vector to be of the empty interface type. And what this is now going to let me do is store any data I want in the vector. Now, you might think that there's a lot of flexibility with that. Oh, wow, wait, I can store anything I want in there? Yeah. The problem is that you can store anything you want in there. It's not restricted to just one type of data. So you can intermix integers and strings and floats. And that might sound great, but remember that all of that data is being decoupled behind the interface. And we never really know what data is being stored anywhere unless we start to use reflection or type assertions again. So the usability of this vector, I think, diminishes. And look at the call to last. It's the same 4 lines of code, but since we're returning the concrete data in a decoupled state, the caller is never going to initially know what type of data they got back until they do more work. And that's where that usability comes from. But once again, it's the same 4 lines of code with the 0 value for the empty interface. So the question then is, implementing this vector with generics, will it add value to our lives? Will it make us be able to write code that's cleaner and more comprehensible and more readable with the maintainability? And I think the answer is yes. Now, I'm going to be doing this throughout the class or talk. I'm going to be removing some of the generic syntax so we can look at it with our Go eyes and then bring it back in. What you see me doing here now is defining a type named vector, which is based on a slice of T, but not T, the concrete type. It has to be T, the generic type, a type to be determined later. And every time you hear me say a generic type to be determined later, then you know that we need our square bracket syntax, because it's that syntax that defines T as a generic type, not a concrete type, and any saying that it can be anything. So every time you're going to see me put these square brackets back in when we need T to be a generic type to be determined later. Now, look at the implementation of last. You can see here that the receiver is based on a vector, but not a vector by itself, because a vector by itself doesn't mean anything. Remember, when we construct a vector, we have to also define, declare infer what t is going to be. And so a vector by itself is not enough. Anytime we're going to reference the vector type, we're going to have to reference it with the square brackets to say a vector of some type. Now, in this case, we're saying of some type t declared here with the type. Since this is a method, this is already bound. In fact, because this is a method, we're not going to do anything like this, like we would with a function, because we're already bound to this type declaration, thanks to the fact that this method is bound to the vector through the receiver. So this isn't necessary. But that being said, anytime we're going to reference this generic, this type vector, which has an underlying type of t to be determined later, we're going to use our square bracket syntax here to reference it. It's okay. And now you can see here on the return, we're also now going to return t. We have to, because if this is a vector of some type t to be determined later, then we got to return that same type t. And there it is. Now you can see that we have the same 4 lines of code right here. Is it empty? If it's not empty, return the value at the largest index position and nil. But if the vector is empty, we want to return the error. And now we got a problem. Because we have to return the 0 value of a t. We have to construct t to its 0 value state in order to satisfy the return. Now, you might think, well, Bill, why can't we just do this? Isn't that 0 value construction? Well, we could use empty literal construction of t if t supported empty literal construction. In other words, if t got substituted for struct type like user, then empty literal construction does result in the 0 value of a user. But guess what? What if t is substituted for the int? This is illegal syntax. You can't use empty literal construction for an int because it doesn't really make sense. Empty literal construction is about assigning a value to something during construction, whether that's a collection or struct type or right. Like we don't have that. Same thing if that's a channel. You don't have it. So we need a universal way of constructing a value of type t to its 0 value state, regardless of what the type is. Now, in the language, there's only 2 ways to do this. The first way is what you see on line 59, and that's using the keyword var. And this is why I teach so much in my classes to use var for 0 value. It is the universal way to construct a value of any type, int, user, whatever it is, to its 0 value state. So what you see me doing is declaring a variable named 0 of type t, constructing to its 0 value state, and then I'm using 0 on the return. This works great. This is the way I prefer to do it. However, there is another universal way to construct a value of type t to its 0 value state, regardless of what t is. And that's the built-in function new. New can construct a value of any type t to its 0 value state. The problem is that it uses pointer semantics and returns the address of that new value. And so we've got to add the dereferencing of that address. We've got to return the value that the pointer points to out. Now, I'm sorry, but even though this would eliminate a line of code, I have a big philosophy about making things easy to understand, not easy to do. And to me, this is easy to do with a lower level amount of reading comprehension on the code. Not everybody's going to quickly understand what we're doing here with the dereference and why. And so, though some people like this because it consolidates it, I'm about easy to understand. And so I like the idea of using var in the 0 variable. So that's what we're seeing there. Now, I've got a vector that can be of any type t. We know that it's got a concrete type, and I think it gets rid of our usability issues that we're going to see with our interface-based version. So let's run this code a little bit. If you notice here, I'm constructing a vector int using my literal construction to initialize the vector with some values. Then I'm calling last, which we know brings back an integer, which is great because then I can do direct checks against that integer, like, is it a negative number? Here's vector string. I can use my literal construction to initialize the vector with 3 strings. I can call last, which we know returns a string. And I can do very specific checks like validate if the string is on UTF-8. And we can print that out. Remember I talked about there's usability issues with our vector interface? Look at this. When I construct the vector interface, I'm storing an int, a string, an int, a string, and a float. Ugh. Right? We're mixing data. Now when I call last, I have no idea what I have. What if I still have to apply those same checks? If it's an integer, do the negative check. If it's a string, do the valid UTF-8 check. If it's a float, I don't know. Here's the problem, that we now need to do a type assertion to figure out what are we dealing with so we can do the right check. The usability is lost here. And this is why I'm excited about generics here. Because as you see on line 107, I can construct a value of type vector and then explicitly tell the compiler, this is going to be a vector of int. And then I'm using my literal construction to assign values to that vector. And now when I call last, what do I know? I know I have an integer. I have to. I've explicitly specified it. I can do the check. Here, same type vector, but this time we say, no, this one's going to store strings. And I can use my literal construction to store those strings. And now we know last returns a string. I can do my check. This code works. We can change into O2, run it. We can see our vector int and our vector string, which means I can take this code, say that we're now going to store float 64. There we are. We would call this gen float. We now know that last has to return a float. We know it returns a float. We know explicitly they can only store floats. We're getting our usability back, right? I don't know what I'm typing today. We're getting our usability back. We can say a negative float. What's also nice is I can use the specific verb. I know I'm working with a float. I didn't do another implementation, but yet we know we have that. And if I didn't make any mistakes, boom, we're now working with floats. Not another implementation, not a consolidation. The same 5 lines of code that we wrote here, or 4, works for all types. Now, some of you might be asking, Bill, do I really have to pass explicitly the type information? Aren't we doing literal construction here? Can't the compiler figure out that it should be an int? Can't the compiler figure out that this should be a float? I mean, the answer is yes. It should be able to figure it out. Well then, Bill, why is it not figuring it out? For one simple reason. The draft that we're exploring tonight has not been fully implemented in the Go tooling. That would actually be, I think, a huge waste of time. We want to explore and settle on the syntax so we can actually spend more time getting it right in the compiler. So there are some things here that have not been implemented, not because they don't want to, just because it's not the best use of time. But in a true compiler implementation, we wouldn't have had to do this if there's literal construction. If you did want to do 0 value construction, well, once again, there's nothing that the compiler has to infer type. We'd have to pass it in. But if we're going to have literal construction, then for sure the compiler can infer. It's just that the current implementation of the tool doesn't have it, but the compiler will. The compiler will. All right. So once we have an actual compiler implementation, this is what's going to work with that literal construction. We're not even going to have to pass it in. Compiler can figure it out, just like it figured it out with the generic functions. Okay. These are our user-defined types that are built on a underlying type. But what about our struct types? We probably declare more of those in our programs than we do these types. Well, let's go look at a struct type. Now, the best way I thought of exploring the struct type was to create a type that would be associated with a container type of algorithm, like a linked list, right? This is where generics are really going to come in handy for us, this first release at least. And so what I decided to do is just construct the beginnings of a linked list implementation that could be generic. This is where, you know, these types of things really hurt us today in Go. Because the bulk of the code we have to write is identical. The only thing that changes is when we're dealing with the data that we want to store. So let's go through that same exercise one more time here. You already know that I want to construct a node that can store data of not just one type, but any type. In other words, we want to store data of type T to be determined later. As soon as I say that, what do we know? Bill, you got to go and add those square brackets so we can define T to be a generic type. And Bill, let the compiler know it can be anything. And now we have the ability to substitute T again for whatever we want, integers, strings, users, whatever it is. Now, when it comes to a linked list, the node has to point to the next node. And in this case, I'm even doing a double linked list, points to the previous node. So we need pointers of this same type of node. But remember, a node by itself doesn't mean anything. A node by itself doesn't mean, it has to be square bracket syntax like on construction, a node of type T. In fact, the same type T. We have to point to nodes that store the same type T of data. And so on these field declarations, what you're seeing is node square bracket T to denote that we need to point to nodes of the same type T. There it is. We saw this when we were doing the underlying type constructions too, right? We saw that with the receiver. Now, here's a list. Again, the list is going to maintain pointers to the first and last nodes of some type T. So list also has to declare a generic type that can be anything, and then we can apply it to our first and last field declarations for a node of type T. Okay, which means that when we construct a list and substitute T, then our nodes will follow along the same type. Now, to make this a little more interesting, I added a method named add. Again, it's a method. So the receiver binds us to the type. And you can see here that we're binding to a list of some type T. And we're accepting data of some type T. And we're returning a node of some type T, where T is declared here at the type level. There it is. Now here's the big win. This is the win. This is the code that always requires us to have different implementations for different types. It's the construction of a node. But we want to construct a node based on the type of data we pass into the add, which is based on the type of data that we explicitly state on the list construction. So we can construct a node of some type T, storing that data in the data field and pointing previous last. And then this is the code that just doesn't change. The wiring up of the nodes, whether it's the first or the last, it just wires it all up. That's the big win. That's the big win. And so we can see that when it comes to our struct types, we're going to apply the generic type identifiers to these fields. We're going to apply these generic type identifiers to our methods, where we can accept data of some type T, return data of some type T, or in this case, a node of some type T. Now, let's see how this kind of all works. I'm going to declare a type named user. That's the data we're going to store in the list. And then on line 55, you see me construct a list set to its 0 value, where this list will manage user data. This is the substitution for T, a user. Here, I'm going to construct a list set to its 0 value, where we're going to work with pointers of type user. This is our value semantic construction. This is going to be our pointer semantic, right, in terms of the data that we're going to be working with. Now, since we said that T is going to work with user values, add accepts user values. Because here we said that we're going to have a list that maintains users based on pointer semantics. Add accepts the address of user values. And we can see that these data fields are going to be value-based and these are going to be pointer-based. All I got to do is run this code. So we'll go into O3. We'll run it. You can see the ampersands here where FUMP is telling us that we're actually working with addresses of that struct value. And right now we've got these two names in it. Nice. Now I'm not going to do this for another type, you get it. But you can see here how we can now start to define these sort of container types and have a single implementation of one, and then be able to reuse the implementation for the different types of data that we want to store. Plus, we can work with values and pointers of those types as well. Okay, brilliant. I've got two more code examples to share with you. And they add some interesting complexity because this complexity exists in the problem set. And that is constraint. I've been lucky so far that everything I've shown you didn't care what we substituted T for, where T could truly be anything. But there are going to be times where there's going to have to be a constraint on what T can be. Now there's two types of constraints here. The first one I'm going to share with you is around behavior. We might be writing functions that assume that the data we're passing in must exhibit a certain method or method set of behavior. And so we have to tell the compiler about that constraint so it can do a compiler check to validate that whatever type we use and whatever data we pass in conforms to that method or method set of behavior. So we're going to start with behavioral constraint here. And I'm going to define two user-defined types, one named user, one named customer. And each of those are going to exhibit a behavior named string that return a string. And these methods really represent the ability to stringify a user or stringify a customer. Why would you ever want to stringify something? For logging. You may want to be able to log a user or a customer, and we'll implement this method named string that returns a string. And now you have the ability to log a user in a format that is compliant with how you maybe do logging. So stringification can be important. Now, to have a little bit more fun, I wrote some concrete functions that can stringify a bulk or a collection of users into a collection of strings. So given this collection of users, you'll get a collection of strings with the stringification with the right user and the right index. And it takes about 5 lines of code to do that. We're going to construct the slice that we're going to return, construct a slice of string of the right capacity by using the built-in function length to determine the length of those users. We're going to then do our linear traversal and for range over each individual user in the collection. And then we're going to call the string method against each user to do the actual stringification work, storing that string into the new slice and returning that out. If we want to do the same thing with customers, I've got to, again, duplicate a lot of that code because now I've got to accept the collection of customers. I'm going to use length again. I'm going to range. I'm going to store the stringification of each customer in the new slice and return it, yada, yada, yada. I want to do it again. I got to write another function. Remember how we started this talk. Is there a way to consolidate all of that? I'm not going to go into this. You've seen it. Yes, I can again write a polymorphic function using the empty interface, and I can do type assertions, but there's still a large amount of code that is duplicated. Okay, can I do this in a generic way today in Go? Believe it or not, I can. I need 13 lines of code and a lot more of the reflect package API. But let's get real. If you're staring at those 13 lines of code like I am, your head is spinning. You have no idea what that code's doing. because it's not really language syntax based, it's API based. Look, just go back to this function here. Can you read that code? Yes, you can. You can look at it and fairly quickly analyze it and understand it. This is not fairly quickly. Even if I break it down, it gets interesting. Empty interface to accept a slice of any type. Reflect value of to do the inspection. Kind, is it a slice? Yes, great. Now we use the method len, not the built-in function len, to construct the new slice. And I have to validate if that data even has a method named string, because if it doesn't, I can't do anything, because we need the string behavior to do the stringification. So now I'm using reflection across each value in this index and then saying, does it have a string method? And if it doesn't, we're done. And if it does, then we can call it. There it is. And then I can take the result of the string call and get it into append. Pretty cool though, actually, isn't it? In reflection, I can call a method at runtime by inspecting if the method even exists. There it is. But come on, this code is going to be very hard to maintain and debug and understand. It's tough. What I want to do is get back to those 5 lines of code that we wrote when we were working with the concrete data, but be able to do that in a generic way. Here it is. Now, once again, I'm going to get rid of this so we can look at it and break it down. I want to write a function called stringify that can accept a slice of some type T to be determined later and return that slice of string. As soon as I say type T to be determined later, what have I been doing all night? Been adding my square bracket, I've been adding the generic type T, and then I've been saying any. And then I'm going to make that slice of string for the return. I can use my language mechanics to do the iteration of whatever T is. I call string here on the append, and I do the return. Now, I've got code here that's going to call these functions, okay? But let's see what happens when I run example 4 right now. Oh, I've got a compiler message. It's about line 114. It's saying that this type T doesn't have any constraint, so we're not sure about the method call here, string. I'm basically not telling the compiler enough information. I've told the compiler T can be anything. It can't be anything. It can only be types whose values will guarantee to have a method named string. Now, let me show you a couple things here first. I can write a function like this if user is defined, assuming user is defined as a struct type, which we did. I used lowercase u, but that's fine. Again, I called this a concrete function because this function asks for data based on what the data is. And when we talk about is, we're talking about the concrete data. I can write this function like this too if I want. Now, func.stringer is an interface. This is an interface that has one active behavior, string, that returns a string. Yes, user and customer have implemented the stringer interface. But on line 114, this is not a concrete function. This is a traditional polymorphic function. Why? Because it asks for data based on what it can do. You see, on line 111, Bill can only work with user values because that's what it's asking for. But on line 114, it can work with both user and customer values because it's polymorphic. It's asking for data based on what it can do. If it can do this string, you may pass it in. Polymorphism means that a piece of code changes its behavior depending upon the concrete data it is operating on. This line of code changes its behavior depending if we pass in a user or customer or something else. This is our traditional polymorphic function. But think about it. The interface is declaring a constraint on what the data can be. It's declaring a constraint on what type of data, what kind of data we can pass in. We can only pass in data that implements the full method set of behavior defined by stringer. we technically have the same problem here. This code is written with the idea that value, which is a value of type T, can string. But there's no constraint. We have to, just like we have to here, constrain with the highest level of precision what the behavior needs to be for this polymorphic function to work. We need to define a constraint to make sure the compiler knows that T just can't be anything, but it has to be of a type whose values can string. Now, since we already use interfaces as our mechanic for defining behavioral constraints, the draft says, why reinvent the wheel? And why don't we use interfaces here as well? Why don't we say that our generic type T is to be constrained to just those types where we can validate at compile time, we'll have data values that we pass in that implement the full method set of behavior defined by stringer. Remember, generic functions are polymorphic too. It's just not a traditional polymorphic function that we're writing at runtime polymorphism, right? This is compile time polymorphism, where we're allowing T to be substituted, but at compile time, where our traditional polymorphic functions are data flowing kind of runtime, right? We do compile time checks to validate, but runtime polymorphism as opposed to this compile time polymorphism. So I think it makes sense to use the interface to apply those behavioral constraints to our generic functions, just like we do to our traditional polymorphic function. In fact, by changing out any and applying the interface fump.stringer, we don't get any more compiler messages. We're good, because the constraint matches the behavior that we need and expect. And now the compiler can do its job to make sure that any function call and any data we pass to this function knows how to string. Okay, kind of cool. But these generic functions bring with it one more type of constraint that we don't have in our traditional polymorphic functions. And that is that we can write generic functions that attempt to use certain types of operations that only apply to certain types of data. What types of operations am I talking about? Things like adding, subtracting, and dividing. These are operations that we don't really have a problem with in terms of our traditional polymorphic functions, but we will with our generic functions, because we're going to have to make sure that whatever we substitute for T can work with those operators. Let me give you an example. Look at the add function for a second. I'm just going to leave this here, right? Let me get rid of this again. What is add saying? Add is saying that I want to accept a value of some type T and a second value of the same type T, add those two values together and return the result of that type T. Now, it's type T to be determined at compile time. So I might just blindly say this, but can T be anything? Well, let's think about it. Can T be an int? Yes, I can use an add for an int. Can T be a string? Yeah, could be a string. Could be a user? No, you can't add struct types together. We don't have this concept in the language, and we do not, and I don't expect to ever have it, operator overloading, where we can implement an operator plus method to even support it. So no, T can't be anything because it can't be a user. Now, I did say that T could be a string here. Can T be a string anymore? No, because you can't subtract strings in the language. So if you see, T can't be anything. However, this isn't based on a method of behavior. I'm not making a method call here. Interfaces declare a method set of behavior. How am I going to give the compiler information that constrains T on an operation when the only type of constraint we have today in the language is behavioral? Ha ha! This is the problem. We need some new syntax. Yeah, this is the second place in the draft where we really do need some new syntax that we don't have today. But we want to really minimize adding anything new. So what does the draft do? The draft says this: let's continue to use our interface to define constraints. However, this isn't a behavioral constraint. It's really a constraint on what concrete types T can be. So what we're going to do is take the interface, and instead of defining a method set of behavior, we're going to declare a type list. And we're going to say that T can only be a type of this set, with the understanding that this set works with this operator. And now we are able to give the compiler the information it needs in order to build these functions out with the highest level of integrity. However, something not so fun happens. You see, does this make sense? Does it make sense? I cannot write a polymorphic function with this interface because our traditional polymorphic functions are not based on data on what it is. It's based on what data can do. This interface isn't defining behavior. It's just clarifying what is. In other words, this sort of breaks interfaces in the traditional sense, because once you define a type list, there is no longer the ability to use this in a traditional polymorphic function. Maybe that's good, maybe that's bad, I don't know. But these types of interfaces, when they're declared with a type list, will only be usable in our generic functions because it's the only kind of place it works. Remember, our traditional polymorphic functions are based on asking for data based on what it can do. Our generic functions are polymorphic, but they still ask for data based on what it is. They're still concrete functions at the end of the day. In this case, we are restricting the set of what is. Now, you can still have interfaces that have both a type list and a method set. I haven't seen a real need for this, but it's possible. I'm still waiting for someone to write a generic function that's applying both operators and behavior in a unique way. Because most of the time, if you've got a method set, then the operations can happen inside the method. At least that's the way it's been for me. And I haven't seen it, but I want you to know it's possible to do that. Okay. Some people have asked for things like adding the type list here or applying operators here. But the problem is that we can only have one constraint per type. And if you do have that mix of needing a type list and behavior, then you wouldn't really be able to do it there. And that would get really hard to read. So if there's anything about the current draft spec that maybe bothers me a little bit, it's this, because it kind of breaks the interface to be used in a traditional polymorphic way. but nobody's come up with a better solution. And it could just be something that we learn to just read, understand, and live with. And it is what it is. Okay, it's 8 o'clock. There's more code here. I'm not going to go through it. It really gives us what we need to look at to understand the bulk of the spec. I do recommend that if you're interested to then go through the rest of the examples that I have there. I've tried to document them really well. And if you run into any issues with them or problems, just send an email to me. I'm going to drop my email here. And share whatever that code is, and I'll try to walk through that with you. And right now, the discussion on the mailing list has pretty much died out. There's some fun discussions on Slack and the generics channel, but I strongly believe that this is going to be the syntax that we're going to see moving forward for August of next year or February 22. Okay, with all that being said, I'm going to open it back up, Carrie. We can ask who's here if they want to spend about 2 or 3 minutes. I'd love to hear everybody's thoughts and or take any questions that you might have. So yeah, Kunal, if you have any questions, or I'd love to hear your thoughts, take it like 2 or 3 minutes on what you saw.
Yeah, I thought that was great. I think kind of repeating the data based on what it is versus what it can do, I think that kind of really clarified some things for me. So I appreciate that. And then I think the only other kind of question I had you already answered, though, was if there's really any upside or downside to explicitly passing the type when the compiler can infer it. But I think you answered that with the second example.
Yeah, we want the compiler to infer it when it can. It just keeps the usability where it is today. But yeah, you get to pass it in, so that's awesome. Awesome. So did you feel like at least some of the code examples, now this can make code harder to read if you continue to walk down some of the code that I have. And there's like a heap implementation. I mean, you start dealing with multiple type identifiers, which you can have in that square bracket list. You can have T, comma, S, comma, K, and you can have longer names, shorter, right? I mean, there could potentially be some readability issues, but I tried really hard to share how if we can eliminate the empty interface in certain cases and type assertions and reflection in some cases, we could get more readable code.
Yeah, I mean, I think there's definitely some power in that and streamlining things. Like you said, you remove the repetitive code that we all write. I like the last two examples, the 4 and 5, using the behavior it supports, like stringify. I think that's pretty cool. And I'm still kind of with you. I don't know how I feel about the last example. I mean, it's neat how they implemented it to ensure that it only acts on those types that where it makes sense. But I don't, again, what other way would you do it? To me, it's almost like you're using the same structure for, in 2 different ways. So you have to be cognizant of that.
Yeah, and I don't know how we'll handle documentation there, because
Right.
An interface might come up, and I guess you would have to know what the method set is for the interface, and you'd see the type list and you'd be like, okay, I can't use this in a traditional polymorphic function. This is just for generics.
Right.
And I expect that they're going to have either some more pre-declared identifiers for these things, like they have one now called comparable. So if you're going to be using the double equal sign, then you just use comparable. And they may even end up with a package in the standard library with a bunch of these types of interfaces that are just going to be common.
Right.
So we won't have to declare them all ourselves. So, I mean, there's work there to do. That's why we're looking at August of next year, because not only is there a compiler implementation, it also has standard library implementation, implications and,
Right.
and things. Early, do you have anything you want to add, share, questions, thoughts?
I think I actually don't have a problem with that implementation, because normally generics, everybody does the brackets, but then like you wrote in your article, that's going to be problematic, since you're going to have to essentially, redo the entire compiler just to get all the quirks. But if you're used to using generic types, I just by when I read the draft and then your article, it jumped out at me. And I did appreciate that. I don't have to think about too much in terms of how the syntax look, from the way I would do a slice to the way I would annotate it in between the function keyword and then the parameter of the function. In terms of so I think it's going to stick, like you said. And in terms of, I think they're probably going to do the same thing Rust does. And you just finished saying it. They're going to most likely implement in their base library a whole bunch of very common types that are used. Generic types interfaces. And that's going to be the way to go. Now, I don't know, is Go, what is the DSL supporting Go?
Say that again. Why is DSL?
What is the domain? Yeah, what is the DSL supporting Go?
I don't know. I don't think there is any
okay,
DSL that I know of.
What I'm saying is that could be one way they could satisfy more users, but not that I'm saying they need to do it. But
yeah, I don't think you're going to see any of that. I think that maybe starts to fall into the meta programming. That's in the admissions list. So maybe in another release, like now you're looking at maybe 22, 23, maybe. If it's,
yeah, but I've worked with generics before, so I was happy. That's why I came. That's what got me excited going back to Go, because of once I found out that, hey, these guys are using generics, because a lot of people that needed generics were, either going back to Rust or NIM, since NIM is a lot more productive than Rust. So I'm excited.
Awesome. Brilliant. No, I'm excited. That's great to hear. I dropped those 3 links. The Google survey is nice. So if you want to send any feedback to what you saw, positive or negative or thoughts, it's anonymous. You can use that Google survey, and everybody there is reading it that's involved. So it's nice. Other than that.